In the last example, we looked at qualitative entropy, and now we're going to do quantitative measurements of entropy. In a quantitative measurement, you need to have standard entropies, and it turns out that the change in entropy of a reaction, just like enthalpy, is the standard entropy of the products minus the standard entropy of the reactants. Products minus reactants. Again, very common thermodynamics thing. When we deal with free energy, it'll be the same way. Products minus reactant. Just to be aware, the units on entropy are joules per mole Kelvin, which will be important later because normally most of our thermodynamic quantities except entropy are reported in kilojoules per mole. Right? So that will require you later to do some calculations. Not right now, but forewarned. So products minus reactants. Entropies are stoichiometric quantities. The more material, the more inherent entropy it has. Same with enthalpy. The more logs, more fire, as I like to say. Same here. So let's take a look at the quick examples. You have calcium carbonate, CaCO3, going to calcium oxide plus CO2 gas. Leave out the states on the solids just for sake of clarity. And it is simple as products minus reactants. In this case, the products are calcium oxide. The entropy associated with is 39.8 joules per Kelvin mole, and there's 1 mole of calcium oxide, plus the carbonate, carbon dioxide, 213.6 joules per K mole. All of that minus the calcium carbonate, 92.9 kilojoules per mole Kelvin. So we add these two together, 39.8. This is 253.4 minus this positive value equals the delta S of reaction, the change in entropy for the reaction under standard state conditions is equal to 160.5 kilojoules per mole of reactant. All right. Straightforward. Just remember, unlike enthalpy, these are stoichiometric quantities. Entropies are not usually non-zero for materials, for elements. So get used to this habit of, oh, the hydrogen doesn't have any enthalpy. True, but it does have entropy. So just be aware of that. And so the same idea of products minus reactants, we have our ammonia, N2 plus 3H2 going to NH3 gas. And we have, the only difference is this time we have to take into account the stoichiometry. So we have 2 times the standard enthalpy of formation, 2 for our stoichiometry, 2 times the standard enthalpy of formation for ammonia is 193 kilojoules, 193 joules per mole Kelvin, times 2 because there's 2 of them, products minus the reactants. The nitrogen has an entropy contribution of 191.5 joules per mole Kelvin, and 3 times the hydrogen's contribution, 131 joules per mole Kelvin. Now, just quick inspection shows a bunch of gases going to less gas. 4 moles of gas going to 2 moles of gas. We'd expect there to be a negative change in entropy, and math looks like it works that way. 386 joules per mole Kelvin minus 584.5 joules per mole Kelvin to give us 1 minus 198.5 joules per mole Kelvin for this reaction. So delta S of the reaction. Last example, so we have some H2 going and plus some chlorine going to make HCl gas. These are all gases. We have our table of thermodynamic quantities, and so it's products minus reactants, because there's 2 HCl, 2 times the standard entropy of formation, 187 joules per mole Kelvin for the HCl, minus the hydrogen's contribution, 131 joules per mole Kelvin, and the chlorine's contribution, 223 joules per mole Kelvin. This is equal to 20 joules per mole Kelvin. This is this part right here, this minus sign, is where the mistakes usually happen. Oftentimes students will change the signs. My suggestion is do all the math here, get a number, 131 plus 223 gives us 354, and that will be equal to this number minus this number. If this had been a negative sign, then you would have to do the correction in that sense. So, take it slow, particularly with the reactants side. So there's a way to quantitatively calculate entropy. Again, notice we can make some good assessments relatively quickly on the sign of our entropy. For the first two, A and B, we could say for sure, oh, one's going to be positive and change in entropy, the other one's going to be a negative change in entropy. But sometimes when the entropy, and there's not a big difference between the products and the reactants in terms of the entropy, it's a little harder. Here we have 2 gases going to another gas. That may be a decrease in entropy, it may not. All right, so, but eyeballing it, does the sign make sense? All right, check your answer.